Hi everyone, how are you all? So before we start, please let me know, am I audible? So in this session we are going to discuss All India Mock Test 5 solutions. We will quickly go through most of the questions of this All India Mock Test, and this is the last mock test for GATE Computer Science 2024 exam. So I hope you loved all the previous AIMTs. This is our final All India mock test for GATE Computer Science 2024 AIMT 5. I hope you loved all the All India mock tests that we have conducted in this year. Okay. So let's start. Let's start with this question. This is a theory of computation question. Let's solve it. Which of the following statements are true for every language L which is subset of 0, 1 whole star? Okay, so the question is asking which statements are true for every language. So you can take any language L. Okay, for every language L, which statement are true? So remember, what is L? L is a language which is subset of 0, 1 whole star, means this 0, 1, this is the alphabet. Okay, what is the alphabet? The alphabet is basically 0, 1. Okay, now let's see. Can I say that every language L star is infinite? What about option A? Can I say that L star will always be infinite? So this option is basically wrong. Okay, because for example, for option A, what you can do? You can take L equal to 5. This is a language. Yes or no? What is L star? What is L star? L star will be set containing epsilon. Yes or no? Okay, so you can see L equal to 5. L equal to 5 means empty language you can take. This is a language, empty language. So L star will be set containing epsilon. Okay, you can see this is a finite set. Okay, you can see this is a finite set, right? Similarly, you can take L equal to set containing empty string. Then what will be L star? Then what will be L star? That also will be set containing empty string. So again, you can notice this is a finite language. This is a finite set. Okay. Now remember one thing, that if you take any other language, then definitely L star will be infinite. Okay. If remember one thing, L is if L is not phi and L is not this language set containing epsilon. Okay, so remember this point, that if L is any other language other than these two, okay, if L is any language other than these two languages, if you take any language, then remember L star will always be infinite. Then L star will be infinite, will be definitely infinite. Okay, so this is very simple. So you can see this statement A, this is a false. Okay, and the counter example is L equal to empty language, L equal to 5. Okay, now let's see this. L is accepted by some DFA if and only if L is accepted by some NFA. Yes, this statement is true. If L is accepted by DFA, then it will be accepted by NFA. And if L is accepted by NFA, then it will be accepted by DFA. Right? Yes or no? If any language is accepted by DFA, then definitely it will be accepted by some NFA. And if any language is accepted by NFA, then it will also be accepted by some DFA. Okay, so option B, that is true. What about the option C? If L is union of two undecidable languages, then L is undecidable. This statement is false. Okay, option C. Let's look at option C. This is false. See why this is false. What option C is saying? Option C is saying that if L is equal to undecidable language union undecidable language, okay, undecidable language union undecidable language. If L is undecidable union undecidable, then L will be undecidable. This is not true. What you can do? You can basically take any undecidable language. See, what is an undecidable language? Undecidable means not recursive, right? Yes or no? Okay, you already know that if L is decidable, you already know that if L is decidable, then you already know that L complement also will be decidable. Yes or no? Decidable languages, decidable means recursive. Okay, means decidable. What is a decidable language? That is same as recursive language. So you already know that if L is recursive language, then L complement also will be recursive. L complement also will be decidable. Okay. So similarly, you can easily see that if L is undecidable, then its complement also will be undecidable, right? Okay, with contradiction you can prove if L is undecidable, if L is undecidable, if L is not decidable, then remember L complement also will be undecidable. You can prove it using the contradiction. What you can do? See, very simple. If L is undecidable, then remember L complement cannot be decidable, because if L complement is decidable, then its complement will be decidable. Yes or no? Okay, so remember very simple point. If L is undecidable, then remember L complement cannot be decidable, because if L complement is decidable, then its complement will be decidable, and that is a contradiction. That is a contradiction, right? Okay, so very simple. You can prove it using the contradiction that if L is undecidable, then L complement also will be undecidable, right? So very simple point that decidable complement will be decidable and undecidable complement will be undecidable. Okay, so this is the simple point. Decidable complement is decidable and undecidable complement is undecidable, right? Very simple. Now what you can do, see, you take any undecidable language. I am telling you, you take any undecidable language L1. Okay, take any, your choice. You can take any undecidable language L1. Okay, then you already know that this is undecidable because you have taken undecidable language, and the complement of L1 also will be undecidable. The complement of L1 also will be undecidable. We have already seen that complement of undecidable is undecidable. Okay, so you can see if L1 is undecidable, then L1 complement also will be undecidable, right? Now what will be L1 union L1 complement? What will be that? See, L1 is already undecidable, L1 complement is also undecidable. So undecidable union undecidable, this is your union operation, this is your union. So tell me one thing, if I do L1 union L1 complement, then what I will get? I will get sigma star. Yes or no? I will get all the strings, I will get sigma star. But this sigma star is regular, every regular language is decidable. Yes or no? Sigma star is regular, every regular language is recursive, every regular language is CFL, every CFL is CSL, every CSL is recursive. So you can see this sigma star is decidable. So you can notice undecidable union undecidable is equal to decidable. Agree with me? So remember this statement, option C, this is a false. Okay, so remember undecidable union undecidable may or may not be undecidable. This is the conclusion. Okay, I have given you counter example for option C. This is the counter example for option C. But remember one thing that if you do undecidable union undecidable, this is the final note, that if you do undecidable language, another undecidable language, this is undecidable language 1, undecidable language 2, if you do their union, then remember the result may or may not be undecidable. The result may be decidable or undecidable. Okay, the result may be decidable or undecidable. Okay, so this is the simple point. Undecidable union undecidable, this is your union operation. Okay, so that the result may be undecidable or the result may be decidable. So this was your option C. Option C is false. What about option D? If L is union of two decidable languages, then L is decidable. Yes, this is true, because recursive languages, they are closed under union operation. Yes or no? Recursive languages, they are closed under union operation. Agree with me? Is this clear? Okay, so very simple point. You already know decidable, union decidable, the result will be decidable, because recursive languages means decidable languages, they are closed under union operation. Okay, so for this question, the question is asking which statement is true. So the answer is going to be option B, option D. Okay, answer will be option B, D. Is this clear to everyone? Please tell me. Okay, so very simple question. Did anyone make mistake in this question? Let me know. Did you make mistake in this question? Yes or no? See, a student is asking, are we considering undecidable as not RE? No, undecidable means not recursive. Undecidable means not recursive. Okay, remember this point, undecidable, that means not recursive. Okay, that means not recursive. And unrecognizable means not RE. Unrecognizable means not RE. Okay, not recursive enumerable. So this is the point. Okay, remember one thing here. See, in this counter example, you can take any, okay, please notice here, you can take any undecidable language and you take its complement. So you want counter example for option C. Okay, you are looking for counter example for option C. This is your option C. Look at option C only. Okay, forget about all other options. Look at option C. Option C is saying that if L is union of two undecidable languages, then L is undecidable. This statement is false. Why this statement is false? I can give you counter example. I can give you counter example. And what is the counter example? The counter example is take any L1 which is undecidable and take its complement. That also will be undecidable. Complement of undecidable is undecidable. Okay, complement of undecidable. Remember, if you have undecidable language, then the complement also will be undecidable. This we have already seen. You can prove it by contradiction. So you can see that if you take any undecidable language, you can take any language. Remember, this can be any undecidable language. That is your choice. Any undecidable language you can take its complement. That also will be undecidable. Now you take their union. Now you take their union. Okay, now you take their union. This is the counter example. This is the counter example for option C, because if you take their union, this will become sigma star. This is going to become sigma star, and this sigma star, that is your, and this sigma star is basically your decidable language. Okay, this is decidable. So I hope you understood this. Okay. Now, can anyone tell me, can I, one more just simple variation I'm asking, can I say not RE, union not RE, can I say that will definitely be not RE? Can I say not RE, union not RE? Okay, let's assume there is a language L1 which is not RE, there is a language L2 which is not RE. Can I say their union will definitely be not RE? Can I say? Please tell me. Can I say that their union will definitely be not RE? Union of not RE, union of two not RE languages, can I say that will be not RE? No, that is also not correct. That is also not correct. That is also not correct. Okay, and what about RE union RE? What about RE union RE? Yes, that will be RE. Remember, RE union RE. If you do recursive enumerable, union recursive enumerable, the result will definitely be recursive enumerable. But remember, if you do not RE union not RE, then result may or may not be result. Remember, the result may or may not be what? May or may not be not RE. Okay, so I hope you understood this point. So I hope you understood what I'm telling you. Because again, what you can do here, see, very simple. You can take basically, okay, one thing you already know, that if these are the, let's assume these are the recursive languages. These are your recursive languages. These are your RE languages, right? These are the RE languages. Now, these are, okay, the outside languages are not RE. Okay, these languages, this is the not RE area. This is the area not RE, right? Okay, so not RE area means this area, this outside area. This is the not RE area. Now, notice one thing, that if a language you have here, please understand, if a language is not RE, for example, if L is here, then either its complement will be not RE or its complement will be RE but not REC. Okay, if L is here, if L is not RE, then remember its complement, either its complement will be this or its complement will be this. Okay, RE not RE complement. So this is what I am telling you, that if you have a not RE language, if you have a not RE language, its complement will be either not RE, or RE but not REC, or RE but not REC. Okay, so remember, very simple point, that not RE complement, you can simply say that is undecidable. In one word, if you want to say that not RE complement is undecidable, that is undecidable. Other than this, you cannot say anything. Not RE complement, if you say that it is not RE, if you say it is not RE, then that will be wrong. Okay, that will be wrong. Okay, so this is the only thing you can say, that not RE complement is undecidable. Now, what you can do, you can basically take this type of not RE language. You can take a not RE, take a not RE language. What you do, you take a not RE language L, whose complement is not RE. Okay, whose complement is not RE. whose complement is also not RE. Okay, so this type of not RE language you take. What you do? You take a not RE language, L, whose complement is also not RE. Okay, this type of language you take. Now you can notice L is not RE. Okay, its complement is also not RE because I am taking this type of language. I am taking this type of not RE language whose complement is not RE. Okay, now if I do their union, that again will be sigma star. And sigma star is RE. And sigma star, that is recursive enumerable. Is this clear? Okay. So these are some variations of this question. So I hope you understood. Okay. Now I will move on. So please tell me, did you understand this question and its variations? From this question, did you understand something new? From this question, did you learn something new? Let me know. Okay, let's move on now. Now let's solve this question. On this question, you can see there are 11 upwards. So I think this question is loved by many students. Okay, I think many students loved this question. This is a very simple graph theory question. Okay, so let's solve it. So the question is basically saying that let G be a simple undirected graph. G is a simple undirected graph on 8 vertices such that there is a vertex of degree 1, there is a vertex of degree 2, there is a vertex of degree 3, vertex of degree 4, a vertex of degree 5, a vertex of degree 6, and a vertex of degree 7. Okay, which of the following can be the degree? The question is asking which of the following can be. The question is asking which of the following can be. Please focus here. Which of the following can be the degree of the last vertex? Select all that are possible. Okay, select all that are possible. Which of them can be degree of the last vertex? Select all which are possible. Okay, so let's solve it. Now remember one thing. This is a simple graph. This G, what is this? This is a simple graph. Okay, simple graph. This is a simple undirected graph. And in this G, there are total 8 vertices. There are vertices, there are edges. Now the number of vertices, that is total 8. Okay. Now you tell me one thing. If there are total 8 vertices, then what is the maximum degree possible in a simple graph? This is a simple graph. Okay. So you tell me, if there are 8 vertices, then in this, what is the maximum degree possible? What is the maximum degree possible? You tell me this point. What is the maximum degree possible? Maximum degree possible will be 7. Yes or no? And this will happen. When this will happen? Maximum degree is possible is 7. And remember, this will happen. This will happen when this vertex is adjacent to every vertex. Okay. So remember, this happens when this vertex is adjacent to every vertex. This happens when vertex with degree 7, when a vertex is adjacent to every vertex. Okay, yes or no? So this will happens when a vertex is adjacent to every vertex. A vertex is adjacent to every vertex. Every other vertex. Agree with me? Okay. So very simple point. This is the maximum degree possible, and this will happen when a vertex is adjacent to every other vertex. Okay. Now look at this question. In this question, we are saying that, see, look at this question. The question is saying that in this G, there are total 8 vertices and one of them has degree 7. Okay, one of them has degree 7. There are total 8 vertices. Look at this line. Please focus on this line that, okay, a vertex of degree 7 is there. There is a vertex of degree 7 and this is the maximum degree possible, remember. This is the maximum degree possible in this graph. Okay, in G, yes or no? This is the maximum degree possible, right? This is the maximum degree possible in G. So this option is gone, right? Option D, that is gone. Yes or no? This option is definitely gone. Okay, agree with me? Next you can see this is the maximum degree possible in G. Okay, this is the degree 7. Now you tell me, can you have isolated vertex? Can you have isolated vertex? See, G has a vertex of degree 7. A vertex of degree 7. Degree 7. Okay. So remember this vertex. Let's call this vertex A. Okay. Or maybe you can call this vertex V. of degree 7. Now you tell me. This vertex is adjacent to every vertex. Yes or no? This vertex will be adjacent to every vertex. So you can see this V is basically adjacent to everyone. Okay, this is adjacent to everyone, right? Okay, so very simple point. This is adjacent to everyone. So you cannot have isolated vertex adjacent to every other vertex. Okay, so we cannot have isolated vertex, right? Okay, so no isolated vertex we can have. So no isolated vertex possible. Okay, so because no isolated vertex possible, so option A is gone. Okay, option A is gone. Now only two options are remaining, that is 3, 4. Okay, now you already know when you see the odd degree vertex, what will come to your mind? When you see odd degree vertex, what is going to come to your mind? Please tell me. When you see odd degree vertex. So remember, when you have odd degree vertex, this is going to come to your mind that. Okay, so very simple point. In any graph, in any simple graph, how many odd degree vertices you can have? Okay, so you already know that in any graph, okay, you can take any graph G. Now tell me, how many odd degree vertices you can have? We can have even number of odd degree vertices. Yes or no? We always have even number of odd degree vertices. Yes or no? Okay, very simple, that we have even number of odd degree vertices, right? Now you tell me, this graph already has how many? So there are total 8 vertices, and this graph already has how many vertices of odd degree? For this graph, it is given. What is given to you? For this graph, it is given that there is a degree 1 vertex, there is a degree 1 vertex, there is a degree 2 vertex, degree 3 vertex, degree 4 vertex, 5 degree vertex, 6 degree vertex, and 7 degree vertex. Yes or no? So these vertices are already given to you. Okay, agree? So this is already given to you. So, and the question is asking what is the degree of the last vertex? Okay, there is one vertex missing. Okay, there is one vertex missing because total 8 vertices are there. Now these are the 7 vertices and these are the degrees. Now you already have how many odd degree vertices? You already have how many odd degree vertices? This is odd degree, odd degree, odd degree, odd degree. So already 4 odd degree vertices. Already 4 odd degree vertices. Odd degree vertices. So can the final vertex have odd degree? Can the last vertex have odd degree? Can last vertex have odd degree? Please tell me. Can last vertex have odd degree? Odd degree? Can it have odd degree? And the answer will be no. Yes or no? The last vertex cannot have odd degree because in any graph, whatever graph you take, we always have even number of odd degree vertices. Yes or no? Even number of odd degree vertices. So this is the simple point. So I can say that this option is also gone. Okay, this 3 is also gone. So finally your answer will be option C. Okay, but I want to tell you one thing here. Actually, I could have made this question more complicated. Okay, see, tell me one thing. We have eliminated odd degree vertices. We have eliminated degree 8. We have eliminated degree 3. So can I say if options were like this, just notice, if I give you some more options. Okay, if I give you some more options, for example, I give you option this one, I give you option this one. Now tell me, can you say that, will you tick it? See, you have eliminated the options and you got the answer option C. Okay, after eliminating ABD, you have eliminated option ABD, right? Agree? So after eliminating the option ABD, you got option C. Okay, you got your answer option C. But I want to ask you a very simple question, that will you directly select 2, 6 also if these options are also there? Okay, additional options I have given to you. Now you tell me what you will do. Will you check something or not? Or will you blindly tick 2, 6? Are you getting my point? Are you understanding my point? See, this question is quite simple. This is easy question because you can eliminate option A, B, D. After eliminating option ABD, definitely option C will be the answer. There is no problem. But I am asking you, if there are some additional options, okay, for example, option this 2, 6 are also there, then what are you going to do? Are you going to select 2, 6 or are you going to check something? Will you check something or will you blindly select 2, 6? Please tell me. Yes, you will check Havel Hakimi. Yes or no? Very good, excellent. So you will check Havel Hakimi. Okay, now what you are going to you are going to check Havel Hakimi, because remember, okay, so please understand, this is the variation. I am asking you variation. I am asking you additional options if they are available to you. If additional options are available, okay, for example, these options like 2, 6, if these options, and also there is 3. Now, okay, we have to check this. Yes or no? Check if these possible. Yes or no? Okay, so check if these are possible. Now what you are going to do, for each you are going to apply Havel Hakimi. Okay, what you are going to do, for each check if simple graph is possible or not. Check if simple graph is possible or not. Yes or no? For each of them you check if simple graph is possible or not. Okay, and for that you can apply the Havel Hakimi. Yes or no? You can apply Havel Hakimi, you can apply. So can I give you this as a homework? Can you do this? Okay, what you can do, basically apply Havel Hakimi. Okay, what you can do, you can apply Havel Hakimi. Okay, so check if these are possible or not, and for that just apply Havel Hakimi algorithm. Okay, so you can take this as a homework. Let me check 4. Okay, I am checking 4. You can check the remaining. Okay, can any of you check 6? Let me check 4. You check 6, and some of you check 2. Okay, so let's do that. Shreyas, can you check 6? Is 6 possible or not? And someone else, please check 2. I am checking 4. Okay, so let's assume I am checking 4. Is 4 possible or not? I am checking this degree equal to 4. Okay, using Havel Hakimi. So what you are going to do? Very simple, just apply the Havel Hakimi. Your graph degree sequence, you write your graph degree sequence, what that will be. You write that in the descending order. Okay, so in the descending order you can write your graph has degree 7 vertex, degree 6 vertex, degree 5 vertex. Already there is degree 4 vertex, and another degree 4 vertex you are putting. Okay, yes or no? Another degree 4 vertex you are putting, degree 3 vertex, degree 2 vertex, degree 1 vertex. These are the 8 vertices. Now let's check. Okay, so some of you please take degree 6. Okay, so let me check. Now you can apply Havel Hakimi. Now you can apply Havel Hakimi algorithm, Havel Hakimi procedure you can apply. Okay, so this method you can apply. Okay, let's apply this. So very simple. In the descending order you can write, this is in the descending order. Okay, now what you can do, you can delete this maximum degree vertex. Okay, when you delete this maximum degree vertex, then what will happen? Then from the next 7 vertices, delete 1, 1, 1, 1. Yes or no? See this degree. Okay, you are deleting this maximum degree vertex, you are deleting. Then from the next 7 vertices, you delete 1, 1, 1. Okay, so what you will get? You will get 5, 4, 3, 3, 2, 1, 0. Okay, now you can forget about 0, no problem. Okay, so again you put this in the descending order. Yes, this is in the descending order. Then again what you will do? Again you delete this maximum degree vertex. From the next 5 vertices, you delete 1, 1, 1. So what you are going to get? You are going to get 3, 2, 2, 1, 0. Okay, and there is extra 0. Okay, so you can forget about that, or if you want you can put it, but you can forget about zeros. Okay, see, because zeros will be isolated vertices. Okay, remember these extra zeros, these are just isolated vertices. You can forget about zeros. You don't have to worry about the zeros. Okay, just forget about the zeros. These are isolated vertices. Okay, these will become isolated vertices. This degree 0 vertex, it will become isolated, so don't worry about it. Okay, again this is in the descending order. Now what you do? You delete this 3. Okay, then from the next 3 vertices you delete 1, 1, 1. Okay, from the next 3 vertices you delete 1, 1, 1. Now again you can ignore this 0. Actually here you can stop. Here you can easily see, yes, this graph is possible, right? Okay, A, B, C. So you can see this graph is very this simple graph is possible. So this simple graph is also possible. Okay, so remember, because this is possible, so this is possible, so this will be possible, so this will be possible. Havel-Hakimi algorithm is basically recursive algorithm. Remember, because for this degree sequence, simple graph is possible. So for this degree sequence also simple graph will be possible. For this degree sequence also simple graph will be possible. For this degree sequence also simple graph will be possible. Okay, so this is the simple idea. So I can say checking degree equal to 4. This is definitely possible. Okay, this is definitely possible. Okay, 6 and 2, they are not possible. Okay, remember. So remember, for this you can easily see 6 and 4, they will not be possible. Okay, for this graph, if you put 6, then that will not be possible, and 4, that will not be possible. Sorry, 4 is possible. Okay, so 4 is possible. You can check 2, 6 are not possible. Okay, so let me do this here. Not possible, not possible. 4 is possible. Okay, understood? Let me know. See, I did not check. You can check 6, 2. I did not check. You can check 6, 2. Okay, so you can see one thing. This question will become very complicated, very big if I give you these options. Yes or no? If I give you 2, 6, 4, if these options I give you, then this question will become Havel-Hakimi question. But remember, I did not give you these options. Okay, in our All India Mock Test 5, in this mock test, I did not give you these options. So you can just simply eliminate A, B, D, and you can simply get the answer option C. Okay, you don't have to worry about 2, 6. But I am telling you that if I give you option 2, 6, 4, if I give you these options, then please apply the Havel-Hakimi and please check whether simple graph is possible or not. Okay, yes or no? So just take care. Now let's move on. So you can see there are 11 upvotes in this question. So I think many students, they loved this question. That is the reason 11 upvotes are there. Okay, whenever you like a question, then please upvote that question on the Gate Overflow website. Whenever you find that, okay, some question is very good, then please put upvote. Okay, please upvote that question. It will tell us that yes, you loved this question. Okay, now let's solve this question. This is a very simple B tree question. A B tree of order M is M-way search tree. So order definition is given or not? Please tell me. The order definition is given or not in this question? In this question, the B tree order definition is given or not? Yes, that is given, because B tree of order M, that is a M-way search tree. Okay, so very simple point. What is a B tree? This question is saying that B tree of order M, that is a order M definition is given to you, that is a M-way search tree. Okay, M-way search tree. So you can see basically the order definition is given. What is order? That is basically the maximum number of childrens. Okay, this is the maximum number of child pointers, maximum number of child pointers per node. Yes or no? So the definition of order is given. Okay, remember. So because you can see M-way search tree is given to you, so that simply means that the maximum number of child pointers per node you can have, that is M. Okay, so that is the order. What is the minimum number of keys that can be stored on the leaf level of B tree of order 20 with 3 levels? And the question is saying root is on the first level. Okay, you want minimum number of keys on the leaf level. Okay, so first of all, the question is saying that you have a B tree of order, how much order? Order 20. Okay, you have B tree of order 20 and there are total 3 levels and the root is at the first level. So you have B tree of order 20. If you have B tree of order 20, and remember order definition is already given to you. What is order? What is order 20? So that simply means order 20 means, okay, what is order 20? Order 20 means maximum how many children you can have. Yes or no? So maximum 20 child pointers per node. Okay, 20 child pointers. Maximum 20 child pointers per node. Okay, so tell me minimum how many child pointers? If these are the maximum 20 child pointers per node, then minimum how many child pointers? Then minimum how many child pointers? minimum number of child pointers per node. Please tell me. Maximum number of child pointers is already given to you. So I am asking you, what are the minimum number of child pointers per node? So that will be 20 divided, that will be actually, I can say m divided by 2 seal value. Okay, so that will be 20 divided by 2 seal value, and that will be 10. Okay, and remember one thing, if you have minimum these many child pointers you have, so minimum number of keys per node, what that will be? Minimum number of keys, minimum number of keys per node. Okay, except root can have one key. Okay, except root, remember root node can have minimum one key, yes or no? So you can see minimum number of keys, how many keys you can have, minimum number of keys, so that will be 10 minus 1, that will be 10 minus 1, that will be 9, yes or no? So these many minimum keys you can have per node. Okay, now let's solve it. So finally we got in this B tree, you got that. Okay, let's see for the root node what you can have. For the root node, what are the minimum, what are the maximum? Okay, see, let me ask you, what are the keys, minimum keys and child pointers? So let me ask you, key and child pointers. So very simple, for the root node, minimum number of keys you can have, that will be, okay, that will be, I can say 1. Okay, yes or no? Because if there is no key, if the root node has no key, then there is no tree. Yes or no? There is no B tree. So you can see the root node can have minimum 1 key and maximum how many? Maximum 19 keys. Okay, because you can see maximum 20 child pointers. In any node, you can have maximum 20 child pointers. So maximum number of keys you can have, that will be 19. 19, yes or no? And the child pointers, what that can be? That can be 10 to 20. For the root node. For the root node, you can have 10 to 20. Okay, for the root node, you can have 2 to 20. So please notice, because this is the root node, so minimum you can have 1 key and minimum you can have 2 child pointer. Okay, so number of keys will be 1 to 19 and child pointers will be basically 2 to 20. Okay, the remaining internal nodes, okay, non-root internal nodes. What about those? If you have non-root internal nodes, what about those? Very simple, number of keys, that is going to be 9 to 19. Okay, and the child pointers, that is going to be 10 to 20. And similarly for the leaf nodes, the same thing, 9 to 19 and 10 to 20. Okay, so this is the simple point. Now let's find out what you want. On the leaf level, you want minimum number of keys. Okay, what we want? Remember, we want minimum number of keys on the leaf level. Minimum number of keys on leaf level. Okay, on leaf level. So for this, what you need to do? If you want minimum number of keys on the leaf level, then you will give minimum number of keys everywhere. You will put minimum number of keys everywhere. Okay, so if you want this, then what you will do? Then put minimum number of keys everywhere. Minimum number of keys, okay, everywhere, in every node. Right? Okay, so very simple, just put the minimum number of keys in every node. Okay, so let's see on the level 1 what will happen. Level 1, that is the root level. Okay, on the level 1 what is going to happen? Very simple. On the level 1 you can have 1 key. Okay, you can put 1 key and there will be 2 child pointers. Yes or no? There will be 2 child pointers. Okay, there will be 2 child pointer. Now you can see on the level 2 how many nodes will be there? Okay, on the level 1 you have 2 child pointer. So on the level 2 there will be 2 nodes. Correct? Okay, so there will be 2 nodes. You have 2 nodes. And remember, you are putting minimum number of keys you are putting. Okay, minimum number of child pointers you are putting. So there will be total how many? There are 2 nodes, and because there are 2 nodes, so 2 multiplied by 10. These many child pointers. Correct? These many child pointers. On the level 3, what will happen? On the level 3, what will happen? Very simple. On the level 3, there are 20 nodes. There are 20 nodes. Yes or no? There are 20 nodes. And remember, in every node, you will put minimum number of keys. There are 20 nodes. Okay, so 20 multiplied by what? These many keys. Okay, these many keys. So your answer will be 180 keys. Your answer is going to be 180 keys. Because on the level 3, how many minimum keys we can put? That is the question asking. Okay, so the question is very simple. That minimum how many keys you can put on the leaf level. On the leaf level, so the answer is going to be 180. Okay, is this clear? Very simple, right? Agree? Is this clear to everyone? Please tell me. Now, let's move on to the next question. Let's solve this computer organization question from the pipeline. And this is, I think this is another beautiful question. You can see there many students, they loved this question. 8 upvotes are there. And there are many comments under this question that this is a beautiful question. Okay. So this is basically related to control hazards. You can see the branch penalty, branch instructions. This is a beautiful question. The question is asking that if you implement predict taken branch, basically branch prediction, or you implement predict not taken branch prediction. So these are two branch prediction techniques. Okay. See, predict taken, predict not taken. These are branch prediction techniques. And if you implement this, then which will be better? The question is asking which is going to be better. Let me tell you, this is a standard question. Okay. See, this is a standard question. I have taken this question from a standard resource. You can easily see this question I have taken. Okay. Predict taken, predict not taken. Okay. Which is better? So you can see which is better. So for this particular machine, which is better? So this question is a standard question that I have taken. Now, I want to tell you, if you do not know what is predict taken branch prediction, what is predict not taken branch prediction, basically, if you want to understand these concepts, if you want to understand, I can say branch prediction techniques and control hazards, then you can watch this lecture number 5. Okay, this lecture number 5 you can watch. I will put the link in the description, but basically on the goclasses YouTube channel, you can go, and the pipeline complete playlist, this pipeline complete course is freely available. The notes are also available. You can see notes are in the description. So you can find the annotated notes also. Now you can watch this lecture number 5, control hazards, branch prediction. Okay, so this lecture number 5 basically you can watch. Okay, now let's solve this question. Let's quickly solve this question. The question is saying that assume an instruction mix of 15% conditional branch instructions are there, 1% unconditional branch instructions are there, 84 other instructions are there, 60% of conditional branches are taken. 60% of conditional branches, they are always taken. Okay. We have 4-stage pipeline where the branch target location is computed in the 3rd stage. The branch target location, please understand here that branch target location is computed in the 3rd stage and branch condition will be checked in the 4th stage. We will check the branch condition. Okay, that we will check in the 4th stage. Assume no other source of pipeline stalls. We want to decide whether to implement predict taken or predict not taken for branch prediction for this machine. Okay, for predict not taken, this line is important. For predict not taken, even unconditional branches are also assumed to be not taken. Okay, for predict not taken, even unconditional branches are assumed not taken. Which of the following is correct? Okay, the question is asking which is better. Basically, what is the CPI when you implement this prediction and when you implement this branch prediction, then what will be the CPI? What will be the cycle per instruction? Okay, so let's solve it. Let's solve this question. So in this, remember there are, in this question, the instruction mix that is given to you. Okay, the instructions that are given to you. So first let's look at the instructions. There are 3 type of instructions are there. Okay, one is conditional branch instruction, yes or no. One is conditional branch instruction. Another is unconditional branch instruction. Unconditional branch instruction. And another is others. Okay, others. Now remember, how many conditional branch? There are 60% conditional branch, 15%. 15% conditional branch instructions are there. 1% unconditional and you can see 84% other instructions are there. Now in this conditional branch also this is saying that how many are taken? 60% are taken and 40% are not taken. Okay, 40% are not taken. So this is the question, and unconditional, this will always be taken, that you already know. Okay, so unconditional branch, this will always be taken, but conditional branch, depending on the condition, either it can be taken or it can be not taken. So you can see 60% of conditional branch instructions are taken and 40% of conditional branch instructions are not taken. So this is the instruction mix that is given to you. This is the program instructions that are given to you. Now the question is saying there is a 4-stage pipeline. In the third stage, we are computing the branch target location, and in the fourth stage, we are checking the branch condition. Okay, and remember, for these instructions, there is no stall. Because of these instructions, there are no stalls. Okay, so the question is already saying that assume no other source of pipeline stalls. So because of these remaining instructions, we don't have any stalls. Okay, so let's solve it. First, you tell me, let's calculate the branch penalty. Okay, let's calculate the branch penalty. Then we can easily solve this question. Let's calculate the branch penalty. This is what we are going to calculate. Okay, you tell me one by one. Branch penalty, when you implement predict taken branch prediction. Okay, this branch prediction we are implementing. Prediction. Okay, so first of all, let me tell you what is this predict taken branch prediction. Okay, this is a branch prediction. First, let me quickly tell you what is this branch prediction technique. Branch prediction technique, that is, one of them is predict taken. Okay, predict taken. The name itself is telling you. The name itself is telling you what this is saying. See, this is saying that just predict, just assume that it will be taken. Okay, means without checking the condition, just assume it will be taken. Okay, always assume it will be taken. Always assume branch will be taken. Yes or no? Always assume branch will be taken. So very simple point. Okay, remember, always assume that branch will be taken. Now let me ask you, let's assume, okay, let's understand this, that always assume that branch will be taken. Let's understand this. Let's assume you are standing here. Okay, now either you can run in this direction or you can run in this direction. Okay, so these are the two directions in which you can run. Either you can run in this direction or you can run in this direction. Yes or no? Okay, so let's consider this. There is a path here and there is a path here. Okay, please understand, very simple point. There is a path here, there is a path here. Now let's assume that in your mind, okay, there is a race going on. There is a race going on. Okay, in a race. Now in this race, you know, there is this kind of race is there, that this person has something. Okay, this person has something and this person will give it to this person. Yes or no? Maybe there is a stick. Okay, there is a stick, something. Okay, this person is running and this person will give this stick to this person, then this person will run. Yes or no? So this is kind of, I can say, race with stick, something like that. Okay, race with stick. Okay, have you seen this? Have you seen this? Let me know. Stick, race with stick, this type of race, have you seen? Okay, so now you notice one thing, that let's assume this person is having, either you have to go here or you have to go here, but let's assume this has predicted taken. Okay, means this is the normal path, and let's assume this is the taken path. Okay, this is the taken path and this is the not taken path. Okay, this is the not, or I can say this is the branching path and this is the non-branch path. Okay, so please understand, let's assume this is the branching path. This is the branching path, and let's assume this is the normal path. Okay, so you can see now some information you will give, basically some information this person will get, and either he can go in this direction or he can go in this direction. But let's assume in his mind he has assumed, maybe with experience, okay, maybe he is experienced, he has assumed that branch will be taken. Okay, he has assumed branching path will I need to run. Okay, I need to run on branching path. He has assumed with experience, maybe with experience. Okay, so he has already assumed that I need to run on this path. So he is already ready. Okay, this person is already ready that I will run on this path. So as soon as this person will give stick to this person, okay, as soon as this person will give stick to this person, now what this person is going to do, this person will immediately run here. This person will immediately run here. Yes or no? Okay. As soon as this stick, what is this stick? This stick is representing the branch target location. This is representing branch target location. Please understand. This stick is representing branch target location. So as soon as this branch target location you will give, what is the target location? As soon as you will give this target location to this person, then this person will immediately run here. Okay, and when the branch target is calculated, tell me, in this question, branch target is calculated where? Branch target address. Branch target address. Okay, this address is calculated when? Tell me. This branch target address. This is calculated in the third stage. Yes or no? This is calculated in the third stage. But remember, branch condition is checked where? When are you checking the branch condition? You are checking the branch condition in the fourth stage. Branch condition. Okay, we are checking the branch condition We are checking the branch condition in fourth stage. Fourth stage. Is this clear? Okay, so very simple, right? Now, you can see we are checking the condition in the fourth stage, but this address, this target address is available in the third stage. Now you will understand this example. In this example, this stick is representing branch target location, branch target address. So as soon as this person will get branch target address, what this person will do, please tell me. As soon as this person will get branch target address, what this person will do? Because this person has already assumed in his mind that branching path will be taken. So this person will immediately run here. Yes or no? This person will immediately run in this direction. Now in the fourth stage, this branch will be checked. This branch condition will be checked in the fourth stage. Okay, in the fourth stage, this branch condition will be checked. Let's assume this person has arrived here. Now what will happen? This is just an analogy. Now what will happen here? Here you checked branch condition. Okay, checked branch condition. And what it turned out? You checked branch condition. Now you tell me, when you are checking the branch condition, what can happen? What can happen? If this branch condition turns out to be true, then what you will do? And if this branch condition turns out to be false, then what you will do? This is the branching path. This is the branching path. Now you tell me, if this branch condition, you checked the branch condition when you are here. Okay, now if this is true, if this comes out to be true, then tell me what will happen? Then you will continue running. Yes or no? Then it will continue running. Agree with me? You are checking the branch condition. If that branch condition is basically taken or true, then it simply means just continue running. Okay, just continue running. Okay, continue running on the branching path. Continue running on the branching path, right? This is what you will do. Continue running. Okay, but remember, if this branch condition turns out to be false, then what you need to do? Then you change your direction and go to the normal path. Yes or no? Then change direction and go to normal path. Okay, change direction, go to normal path. So this analogy, I hope you understood. Okay, so I hope you understood this analogy. Now let's solve it. Okay, so predict taken. Did you understand what is predict taken and what is predict not taken? So in the predict taken, we are assuming that we are assuming that branch will be taken. Okay, branch will be taken. We have a pre-assumption. Okay, this is a pre-assumption. So here in this predict taken, we have a pre-assumption. There is a pre-assumption that branch will be taken. And there is predict not taken. And there is a predict not taken. In that, what will happen? In the predict not taken, what will happen? Here it will happen that you have a pre-assumption. You have a pre-assumption that branch not taken. Yes or no? Your pre-assumption that branch not will be taken. Okay, branch will not be taken. Not be taken. will not be taken. Is this clear? Okay, so you have a pre-assumption that branch will not be taken. So very simple. These are the pre-assumptions, remember. These are pre-assumptions. Now let's solve it. Okay, so in the branch taken case, what will happen? In the branch taken case, what is going to happen? And in the branch not taken case, what will happen? Let's see. Okay, so predicate taken. In this predicate taken case, what will happen? You have a pre-assumption, then branch will be taken. Okay, so for conditional branch, okay, let's assume there is a conditional branch penalty. First, let's find out conditional branch penalty. Okay, you tell me conditional branch penalty, what will happen? See, let's assume there is a conditional branch here. This I1 is a conditional branch. Okay, this is a conditional branch. Is this clear? This is a conditional branch instruction, this I1. And let's assume there is I2, let's assume there is I3. And let's assume this target address, please understand this target address, conditional branch. And let's assume this target address is Y. Okay, this target address is Y. And this is the target address. Okay, so remember this Y. What is this Y? This Y is the target address. Okay, and when it will be available? This target address, when it will be available? In third stage. Yes or no? In third stage, this will be calculated. This will be calculated. In third stage, it will be calculated. Agree? So this is the target address. Now you tell me. This is the pre-assumption. Predicate taken. This is the pre-assumption we have made. Okay, in our mind, we have this pre-assumption that branch will be taken. Okay, now you tell me, when this instruction, there is a 4-stage pipeline. This is the 4-stage pipeline. Stage 1, stage 2, stage 3, and stage 4. This is a 4-stage pipeline. When this I1 instruction is here, tell me which instruction you will put here. Let me know. Please let me know which instruction you will put here. When this I1 instruction is here, which instruction you are going to put here? Remember, in this stage, we don't know the target address also. So you cannot put this instruction. Agree with me? Okay, yes or no? See, very simple question. In this stage, in the second stage, we don't know the branch target address. This branch target address, we don't know. This branch target address will be available in the third stage. Okay, this is given in the question that branch target address will be computed in the third stage. So when this instruction, this conditional branch instruction, when this is in the stage 2, then you can see, okay, then I2 will come in the pipeline. Yes or no? I2 is going to come in the pipeline. Very simple. Okay. So now this I1, when this I1 is here, now the branch target address will be computed. Here the branch target address will be computed. But here you can say I2 has come, I3 has already come. Okay, I2, I3, they have already come. Now you tell me, in this stage, this target address will be available. Now you tell me, we have pre-assumption that it will be taken. Now what we will do? Will we wait for the condition to check? Are you going to wait for condition to check? In your mind, you have this assumption that branch will be taken, means I will go to the address Y. Now as soon as this address Y is available, this is a stick. This target address is your stick in the previous example. Okay, in this race example, you can notice this was the stick. This target address was the stick. So as soon as you will get this stick, what you will do? You will run according to your assumption. According to your pre-assumption, you will run. Agree with me? Okay. So just let me know. Please give me some reply. Are you getting this point? Okay, so very simple. So here, this is what I'm saying. When I1 is in the third stage, okay, then this branch target address is available. Now we have this pre-assumption that branch will be taken. Okay, this is the branch prediction we have predict taken. So in this situation, what you will do? In this situation, what you are going to do? Very simple. You will fetch this Y. Yes or no? You will fetch this Y. As soon as remember this Y is available, you will fetch this Y. Okay, you will flush these instructions, you will flush, and what you will do? You will fetch this Y. Okay, agree? Now remember, if your decision is successful, now there will be two cases. You tell me, there will be two cases. If your decision is successful, if branch is actually taken, then how many penalty, and if branch is not taken, then how many penalty? Yes or no? Now you tell me, if branch taken, then how much penalty, and if branch not taken, then how much penalty? Okay, so this is what I'm asking. This is what I'm asking, that basically if condition, if branch actually taken, then how much penalty? Then there is only 2 cycle of penalty. Yes or no? There are 2 stalls. Only 2 stalls. Okay. If branch is actually taken, means if your decision is correct, if your decision is actually correct, then there will be only 2 stalls. But if your decision is not correct, then how much? If branch not taken, then how much? If your decision is not correct, if branch is not taken, then how much? Please tell me. So in this situation, what you will need to do? Okay, in this stage it will be known. Remember, it will be known in this stage. In this stage you will get to know, okay, the branch is not taken, my decision was wrong. So 3 stalls, there will be 3 stalls. Yes or no? Because in this stage the branch will be checked, or the condition will be checked. The condition you will check. Okay, so there will be 3 stalls. Agree? So very simple. So this is for conditional branch instruction. Now you similarly you can do for the remaining. Okay, for unconditional branch, what will happen? For unconditional branch, tell me. For unconditional branch, let me know. Unconditional branch. In this situation, what will happen? How many stalls will be there for the unconditional branch? This is S1, this is S2, this is S3, this is S4. Okay, so in this case, again very simple. When this instruction, this is the unconditional instruction, let's assume this is unconditional instruction. Okay, so in this stage, this address will be available to you, this branch target address will be available to you. Okay, now unconditional, this is same as, can I say this is same as taken conditional branch? Yes or no? Okay, can I say that this unconditional, this is similar to what? Unconditional branch. This case is similar to what? Okay, this case, remember, this unconditional branch case is similar to what? Is similar to successful conditional branch case. Yes or no? Successful conditional branch case, or I can say taken conditional branch case. Conditional branch case, right? Because unconditional branch will always be taken. Unconditional branch, that will always be taken. Okay, that will always be taken. So you can easily see that here in this case, how much penalty will be there? In this case, remember, here the address Y will be available. Okay, and you have already, this pre-assumption you have that the branch will be taken. Okay, so remember, you will have only 2 stalls. Yes or no? You will have only 2 stalls, because this unconditional branch, this case will be similar to successful conditional branch case or taken conditional branch case. So here number of stalls, how many stalls? That will be only 2. Okay, so very simple. Now finally you tell me the answer for predict taken. Okay, now you tell me the final CPI for predict taken. For predict taken branch prediction. Okay, for predict taken. Okay, so tell me what will be the CPI? Very simple. Very simple. There are 60%. There are 60% conditional branch instructions. So I can say 0. Remember, for a normal instruction, there will be 1. Okay, this is the normal CPI. Okay, this is the ideal CPI, I can say. That every instruction will take 1 cycle. That is the ideal CPI. Okay, plus. Now, let's see in case of conditional branch what will happen, and in the case of unconditional branch what will happen. Now, these are the conditional branch penalty and the unconditional branch penalty. Unconditional branch penalty. So let's see conditional branch penalty and unconditional branch penalty. So tell me unconditional branch and conditional. So in the conditional branch, you already know that 0.60, these 0.15, 0.15, these many conditional instructions are there. Out of them, these many are taken. So this is the taken. These are the successful ones. Okay, so let me call this successful. This is actually successful or taken. This is actually successful or taken. So in this situation, successful or taken, in this situation, how many stalls? There will be 2 stalls. Yes or no? There will be 2 stalls. Plus, okay, conditional branch when unsuccessful or not taken. Not taken or unsuccessful. Okay, unsuccessful. So in this situation, how many? Very simple. Remember, these many are not taken. Yes or no? These many conditional branch instructions are there. Out of them, these many are not taken. These many are not taken, multiplied by 3 stalls. We have already seen. Okay, 3 stalls. And plus, there will be plus conditional, unconditional branch. Okay, for unconditional branch, what will happen? That is only 1%. Only 1% instructions are unconditional, and they will give you 3 stalls. Okay, they will give you 3 stalls. So this is the case for unconditional. This is the case for unconditional branch. Okay, so your final answer is what? So CPI for predict taken. CPI for predict taken. What that will be? That will be 1 plus, okay, 0.15 multiplied by 0.60 multiplied by 2. This is for conditional success, plus 0.15 multiplied by 0.40 into 2. This is conditional unsuccess, plus 0.01 multiplied by 3. Okay, this will be for unconditional. You can calculate this value. How much is this? Can anyone tell me? Can anyone tell me how much is this? Let me know. How much will be this answer? Can anyone tell me? Okay, just calculate. Just calculate. I think it will be 1 point. Anyone want to tell? 1.30 or 37, something like that. So let me just see the calculation. So you can see I think it will be predict taken. You can see, okay, this is the answer. Assume taken branch penalty. Okay, that will be this plus this one, this plus. Okay, in case of unconditional, there are 2, right? So that, okay, sorry. In case of unconditional, how many we got? In case of, yes, unconditional. In case of unconditional, we got 2 stalls. Okay, sorry for that. In case of unconditional, remember, in case of unconditional, we got 2 stalls. We got 2 stalls. In case of unconditional, we got 2 stalls. We already got 2 stalls. So we got 2 stalls in case of unconditional. Okay, so it will be 1.38. This will be the CPI. Okay, now let's see for the predict not taken. For the predict not taken, what will be the answer? Now, in this case, you tell me successful branch will give you how much and unsuccessful branch will give you how much. See, now you tell me, just tell me taken conditional branch will give you how many stalls? Taken conditional branch will give you how many stalls? Not taken conditional branch will give you how many stalls? Not taken conditional branch is going to give you how many stalls? And unconditional branch is going to give you how many stalls? Okay, how many stalls? This is what I am asking. How many stalls these will give you? Okay, so your case, remember what is your case? Your case is predict not taken. Now we are looking at predict not taken. And this is actually very simple. You tell me, for conditional branches, you tell me first. First, I am asking you for conditional branches. See, just for understanding, again, I am telling you, let's assume this I1 is your conditional branch. Okay, let's assume this I1, this is your conditional branch instruction. Okay, and this is the target Y. And this instruction I2 is there, this instruction I3 is there, and so on. And this Y is there. Okay. So, and there is this pipeline. This is your pipeline, that is S1, S2, S3, S4. There are total 4 stages. Okay, we have total 4 stages. Now please tell me, okay, so what you will do when this when this I1 is here, this conditional branch, when this I1 is here, then in the pipeline what you have I2, you have I3, yes or no? Very simple. Agree? Now you tell me, what is our pre-assumption? What is our pre-assumption? Our pre-assumption is predict not taken. That is our pre-assumption. Yes or no? It is our pre-assumption that predict not taken. Means this is our pre-assumption that you will go to the normal path. This is our pre-assumption that you will go to the normal path. Now, if you are successful, if your prediction is successful, means if branch is actually not taken, then tell me, then do you need to do anything? If branch is actually not taken, then remember I1 is here. When I1 is here, then I2, I3 are here. And this is your prediction. You have this prediction that branch will not be taken. Branch will not be taken. So your prediction is successful. Yes or no? Here you have a successful prediction. Here you have a successful prediction. In the case of successful prediction, you tell me, there is no problem. Yes or no? Here there will be zero stalls. There will be zero stalls because everything is perfect. You don't have to flush anything. Yes or no? I don't have to flush anything. Do you need to flush I2, I3? Please tell me. Do you need to flush I2, I3? Do you need to throw I2, I3 from the pipeline? Is there any need to throw I2, I3 from the pipeline if the branch is actually not taken? Means your prediction is successful. Then there is no problem. So in this case, there will be zero stalls. Okay. Now you tell me, if branch is taken, okay, your I1, when I1 is here, in this situation, I2 is here, I3 is here. Now, if branch is actually taken, your prediction is wrong. Yes or no? Unsuccessful prediction. So in this situation, you tell me, you made unsuccessful prediction. Now in this situation, you tell me, in this situation, I can say that what you will do when I1 will go here, okay, then you will find out, okay, I should go to there. Yes or no? See, when I1 will go here, then I2 will be here, I3 will be here, I4 will be here. Now in this situation, you will find out, here the condition you will check. Here you are checking the condition. Yes or no? Here you are checking condition. Now when you check the condition, then you will find out that you should have taken, means you should have gone to Y. Then what you will do, you will flush. Okay, these instructions you will flush and you will fetch Y, and you are going to fetch Y. So in this situation, there will be 3 stalls. In this situation, we are going to get 3 stalls. Okay, so very simple. And what about the case unconditional branch? Okay, what is going to be the case of unconditional branch? Unconditional branch. In this case, what will happen? In this question, one line is given to you. You can see this statement. Okay, see this line. The question is saying that for predict not taken, please notice this line. For predict not taken, even unconditional branches are assumed not taken. This line you see. For predict not taken, even unconditional branches, even unconditional branches are assumed to be not taken. Okay, remember, unconditional branches also we will assume to be not taken. So this statement actually is given to you. You can see here also. Even unconditional branches are assumed to be not taken. This is a standard question from a top university. Okay, so this is a beautiful question. You can see in this question you can learn a lot of things you can learn. And this type of questions have come in the GATE exam many times. Okay, so you can see this. So you can see this line is given to you that for predict not taken, even unconditional branches are assumed to be not taken. Okay, so how many stalls will be there? How many stalls you will get? So you are going to get 3 stalls. Okay, what you are going to get? You are going to get 3 stalls. See, why 3 stalls? Because the question is already saying that. Okay, question says that, okay, for predict not taken, that when you are predicting that the branch will not be taken. Okay, so remember, for predict not taken, even unconditional branch is also not taken. Even unconditional branch is assumed to be not taken. To be not taken. Okay, is this clear? So remember, for predict not taken, even unconditional branch is also assumed to be not taken. We are going to assume that unconditional branch is also not taken. So it basically simply means that when you have I3 here, okay, sorry, when you have I1 here, this unconditional branch instruction, when you have here this unconditional branch, okay, so when you have this unconditional branch instruction here, then basically you are going to assume that it will not be taken. You are going to assume that it will not be taken. Is this clear? For predict not taken, even unconditional branch is assumed to be not taken. Is this line understood? Please tell me. So remember, when I1 is here, then only the target address is available at this point of time. When I1 is in this stage S3, in this stage only the target address is available. But we are saying that in this case, predict not taken, we are going to assume that it will not be taken. Okay, are you getting my point or not? Is this point clear? This thing is given, this line is given in the question. And this is a standard question. In the standard question also this line is given. Okay, so did you understand that in this stage S3, this target address will be available to us. But we are saying that when you are using this predict not taken branch prediction, then in this predict not taken case, even the unconditional branch, we will assume that it will not be taken. So remember, we have this branch target address, but we will assume that it will not be taken. So how many stalls will be there? So basically, number of stalls will be 3. Yes or no? Because we will assume that it will not be taken. Okay, we will assume that it will not be taken. So that is the reason number of stalls will be 3. Yes or no? Okay, why? Why? Because we assume not taken. Yes or no? We assume it will not be taken. Okay, yes or no? I hope you understood this. So finally, you can see that taken conditional branch, in this situation, there will be 3 stalls. Not taken conditional branch, 0 stalls. And unconditional branch instruction, 3 stalls. Okay, so what will be the CPI? Now let me know the CPI. Now let's find out the CPI for predict not taken. For predict not taken. So what will be the answer? CPI for predict not taken, that will be 1 plus. That will be 1 plus. You can see 0.15 multiplied by 0.60. In this situation, there will be 3 stalls. Yes or no? In this situation, there will be 3 stalls. These are the taken conditional branch. These are the taken conditional branch stalls. Right? Okay, so in this situation, there will be 3 stalls plus 0.15 multiplied by 0.40 multiplied by 0. Okay, this will be not taken conditional branch. Not taken. This will be not taken conditional branch instructions. Conditional branch stalls. Okay, and plus 0.01, these are the unconditional multiplied by 3. These are the unconditional. Okay, these are your unconditional branch stalls. So you can calculate this. What will be the answer? Can anyone tell me? What is going to be the answer when you calculate this? So here you can see that CPI for predict not taken. CPI for predict not taken, that is 1.30. It will come out to with 1.30, I think. Okay, and CPI for predict taken, that came out to be what? Predict taken, that came out to be 1.38. So which is better? So for this particular, so So I can say, so for this particular instruction mix, so this for this particular machine, okay, so for this particular machine, which is better for this particular machine, or I can say for this particular instruction mix, for this particular instruction mix, I can say that which is better. Okay, so I can say predict not taken better. Yes or no? Predict not taken, that is better. Is this clear? A student is asking, what would the number of stalls will be if there is branch target? Will it be 2 stall cycles? See, if this condition is not given, okay, see, please notice, if this condition in the question, if this is not given, then it will become a kind of ambiguous question. If this statement is not given, because you are predicting that it will not be taken. Yes or no? Are you getting my point? If this line is not given, then this question will become a bit ambiguous. Why it will become a bit ambiguous? Then you can take, here you can take number of stalls equal to 2 also, you can take 3 also. Because what will happen? See, you are assuming that it will not be taken. So the answer should be 3. The number of stalls should be 3. But it is unconditional branch. So it will always be taken. So you can take 2. Yes or no? Agree? So this is what I am saying. So that is the reason, if this statement is not given to you, then in this situation, here this will become ambiguous. Then you can take 2 also, you can take 3 also. Okay. So please tell me what will be the answer here. So you can see, for this question, predict not taken is better for this machine. Okay, yes. So this option A is correct. Okay. So predict taken is CPI is, so for both of them CPI is 1.38, that is wrong. For both of them it is 1.30, that is wrong. Okay. So the answer will be option A. For this question, the answer is going to be option A. Okay. This type of many questions I have done in this video. In this video, many this type of questions I have done. Okay, you can watch this video. This is just a control hazard video. You can watch this type of many questions I have done, including the GATE previous year questions. Okay, so you can just watch it. Okay, so I hope you understood. Please tell me, did you understand this particular question? Let me know. Did you understand, and can you solve in the GATE exam if some question comes on predict taken branch prediction, predict not taken branch prediction? Then tell me, please tell me, can you solve it? Did you understand what is predict taken? In the predict taken, we assume that branch will be taken, and there is predict not taken. We assume, we have a pre-assumption that branch will not be taken. So this is just a pre-assumption. These two techniques, these two branch prediction techniques, predict taken, predict not taken, these are basically static prediction. Static prediction means in our mind we have a pre-assumption. What will happen? We have a pre-assumption. We don't care about the situation. We do not care about the situation, what is happening. We have a pre-assumption what will happen. So these are basically static branch prediction techniques. Okay, both of them. Now, let's move on. Let's solve this question. This is a very simple question from the disk scheduling. Actually, this question is little bit different from the typical disk scheduling question. In a typical disk scheduling question, the question will ask you how many track movements will happen, yes or no? Agree? So remember, in a typical disk scheduling question, basically the question will ask you how many seek will happen, or I can say how many tracks you will basically go through. Okay, how many tracks you are going to go through. So, but in this question, the question is asking that in these scheduling algorithms, which of them for this sequence, which of them will give you the same sequence of writes. Okay, see, the question is not asking you how many tracks. Okay, the counting, you don't have to count the tracks. Are you getting my point? Okay, which scheduling algorithm will go through how many tracks, that you don't have to calculate. The number of seek you don't have to calculate in this particular question. In this particular question, basically, read this question. In this question, you have to find out which disk scheduling algorithm will give you the same sequence of writes. Okay, means these requests are given to you. These are the requests. These are the requests, you can see. Okay, now which of them will will process these requests in this sequence. This is what the question is asking you. Okay, which of them will yield the following sequence of writes? Okay, these are all of them are actually write operations. So you can easily see this is given to you in the question that at a particular point of time, the buffer case has dirty data that needs to be flushed to the disk. Suppose that identities to these blocks can be listed in track comma sector. These are the track comma sector. Okay, so the disk head is currently at the track 20. Which of the following disk scheduling algorithm will yield the following sequence of writes? Okay, so this is what the question is asking. Now you tell me one thing. Do you want to know the upper limit? Will it matter the upper limit? Like for example, the scan algorithm. For this scan algorithm, the upper limit matters or not? How many cylinders are there? Does it matter? Does it matter how many cylinders are there? A student is saying that upper limit, lower limit should be given. But does it matter? In this particular question, the how many maximum cylinders you have? Okay, what is the upper limit of the cylinder? What is the basically upper bound of the cylinder number, lower limit of the cylinder number? Does it matter in this question? Let me know. Does it matter? We are just asking you that these are the requests. See, this is a standard question. First of all, let me tell you this question. This is another standard question from a top university, and this is little bit different. This is little bit different. See, why do you want the a student? You can see this is a comment here. I got this comment. Okay, so there is a comment here that the upper limit should be given for the scan algorithm. For the scan algorithm, basically what the maximum cylinder number, minimum cylinder number, that should be given. Upper bound of the tracks, lower bound of the tracks must be given. But is it necessary? Is it necessary? We are not asking number of seek. Yes or no? We are not asking that. The question is asking which of the disk scheduling algorithms yield the following sequence of writes. Means in this order they will write. These requests will be processed in this order. Okay, the question is asking that these requests will be processed in this order. These requests will be processed in this order. Will be processed or served in this order. In this order. Okay, so here actually it does not matter. Scan algorithm and look algorithm, they will give you the same result. Yes or no? Agree? See, scan algorithm and look algorithm, they will serve the request in the same order or not. Notice one thing. Scan algorithm, look algorithm, they will always serve the request in the same order. They will always serve request in the same order. Requests in the same order. Yes or no? Is this clear? Please tell me. Is this understood? That scan algorithm and look algorithm, they will always serve the request in the same order. The request will always be served in the same order, whatever you do. Okay, for example, let's assume this is the minimum cylinder number, and let's assume this is the maximum cylinder number, and let's assume currently you are here. Okay, let's assume they are going upward. Okay, let's assume they are going upward. In the upward direction they are going initially they are going in the upward direction. Now let's assume initially you are at this 53. Okay, this is your initial. Now you can easily see if these are the requests. For example, one request is 14, another request is, let's assume maybe another request is 29, another request is 101, another request is 151. Now you can easily notice that they will serve both of them. In this situation, what scan will do, what look will do? Tell me, what scan is going to do and what look is going to do? Remember, the scan, what the scan will do? Scan will basically go like this. Yes or no? Scan will go and it will go till here. Okay, it will serve this, then it will serve this, then it will serve this, then it will go, and then finally it will come back, then it will serve this, then it will serve this. Yes or no? Like this. Okay, so this is the point. Agree? Now what look will do, what the look algorithm is going to do, the look algorithm is going to do this. It will serve this, then it will serve this, it will serve this request. Okay, then it will not go till the end. This is the last request in this direction. Okay, in this direction, this is the last request. So now it will go in this direction, it will serve this, it will serve this. But notice one thing. See, how many track movements are there? That is different. Yes or no? In both the cases, in look case, in the case of look, in the case of scan algorithm, how many track movements are there? That is different. Yes or no? But the order is same or not? Okay, let's call this request A. Let's call this request B, C, point D, E. So here also you can notice A, B, C, D, E. Okay, yes or no? And here also you can notice A, B, C, D, E. Are you getting my point? Here also A, B, C, D, E. So this is what I am saying. I hope you understood. That order in which they will serve the request, that is always same. So now you tell me, is this question clear? That we don't need. See, actually there is a comment here. On this comment, on this question there is a comment, and there are 7 upward. That is the reason I found this important to share with you. Okay, I thought that this is important, that I should share this, that we don't need the upper limit and lower limit, the maximum cylinder number, minimum cylinder number, we don't need, because we are not calculating the number of track movements. Yes or no? Number of track movements we are not calculating. We are simply calculating that what the order in which request will be served. Yes or no? So is this clear now? That we don't need the maximum cylinder number, minimum cylinder number, these things we don't need, because scan algorithm, look algorithm, they will always serve the request in the same order. Similarly, C scan algorithm and C look algorithm. Similarly, C scan algorithm and C look algorithm, they will also serve in the same order. Yes or no? They will also serve request in the same order. The number of track movements can change. Yes or no? But they will serve in the same order. Okay, understood? Is this clear? So C scan, C look, they will serve request in the same order, in the same sequence, in the same order. Okay, same order, or you can say same sequence. And this scan and look algorithm, they will serve in the same order. Okay, yes or no? Now you can just simply see which of them will serve, will give you the same sequence of writes. The question is asking same sequence of writes. Please notice, the question is asking same sequence of writes, means in which order you are going to serve these requests. Okay, so you can just check it out. Okay, I have already given you the solution. Now you can check the solution and you can see what will be the answer. Is this clear? This is the solution, you can check it out. Okay, because now this is the easy question, very easy question. You can just apply the SSTF, you can apply the scan algorithm, look algorithm, C scan, all these things you can apply and you can see. Okay, so this is the solution, you can check the solution also. I have already given the solution on the GateOverflow website under this question. Okay, so under this question already solution is provided, but this particular point I wanted to discuss. Okay, so now let's move on. Now let's solve this question. This is a simple question from the digital logic. So let's read this. Consider the shift register. Consider the shift register circuit shown in the below figure. Okay, in this figure there is a shift register that is given to you. Assume that I1, I3, I2, I1, I0, that is 0, 1, 0, 1 has been loaded in the 4-bit register using the parallel load mechanism, that is shift equal to 0. See what this question is saying. Notice one thing. If I make shift equal to 0, then what will happen? Tell me. If I make shift equal to 0, what will happen in this circuit? See, this circuit is given to you. In this circuit, if I make shift equal to 0, then what will happen? I3, I2, I1, I0, that is 0, 1, 0, 1. I3, I2, I1, I0, that is 0, 1, 0, 1. Okay. Now, if I make shift equal to 0, then what will happen? Please tell me. If I make shift equal to 0, these are the multiplexers. This is your multiplexer. This is a 2 by 1 multiplexer. This is a 2 by 1 mux. So if I put this shift equal to 0, in this situation, what will happen? Select line, you can see this is the multiplexer select line. So this shift signal, this is connected to the multiplexer select line, yes or no? This is shift signal, please understand. This is shift signal, this is connected to multiplexer select line. Okay, so if I give you this 0, then what will happen? In this situation, what will happen? In this situation, I3 will be loaded here, yes or no? Okay, I3 will be here, I2 will be here, I1 will be here, I0 will be here. So basically, in this circuit, okay, because you can see, if I give shift equal to 0, if I put shift equal to 0, this is a multiplexer, this is a 2x1 mux, select line equal to 0. So you can see this input, okay, this input will go to the output of the multiplexer, yes or no? This input will go to the output of multiplexer. So I can say here what you will get I3. Similarly, when shift is 0, then this input of the multiplexer, this 0 input, it will go to the output. So it will become I2. Similarly, it will become I1, and here it will become I0. So you can see we have loaded the multiplexer. This is a D flip-flop. This is a D flip-flop. So this register we have loaded with 0101. This is what the first line says. I hope you understood what the first statement is saying. The first statement is saying that consider the shift register circuit, assume I3, I2, I1, I0, that is 0101, that has been loaded, that is already loaded, don't worry about it. You don't have to load, that is already loaded, has been loaded in the 4-bit register using parallel load mechanism by making shift equal to 0. Okay, so this is already done. You don't have to do it. I am just telling you how shift equal to 0 can be used to load. Yes or no? If you put shift equal to 0, then you can load this register. This is a 4-bit register. There are 4 flip-flop, you can see. You have 4 flip-flop. There are 4 D flip-flop. So this is a 4-bit register. Now, if you put shift equal to 0, then you can load this register. Okay, you can load this 0101 in this register. So the question is saying that this has been loaded with 0101. Okay. Now notice one more thing. As long as shift equal to 0, this will keep happening. Yes or no? If I make this shift equal to 0, as long as this will be 0, please understand, as long as this is 0, this will be permanent I3, this will be permanent I2, this will be permanent I1, and this will be permanent I0. Yes or no? Whatever I3 you take, so this will be permanent I3, this will be permanent I2, this will be permanent I1 and permanent I0. Yes or no? Agree? Okay. So very simple. As long as shift is equal to 0. I hope you understood. So this is what I am saying, that as long as, okay, so let me write it here. You can easily observe this, that as long as this shift input signal, this is equal to 0, then what is going to happen? Okay, then this will happen that Q3, Q2, Q1, Q0, this will be I3, I2, I1, I0. Means your register content will be I3, I2, I1, I0. Yes or no? So as long as shift equal to 0, I can say register content. What will be the content of the register? The register content will be I3, I2, I1, I0. So this will be the register content. Okay, now the question is saying, read the question. The question is saying that after the data has been stored in the register, you have already stored the data in the register, so there is nothing to worry about it. Okay, already this data is here, this I3 is here, I2 is here, I1 is here, and I0 is here. Okay, so after this data has been stored in the register, for how many consecutive positive edges of the clock signal we need to keep shift equal to 1, so that this 0 detect will become 1. Okay, so that this 0 detect signal will become 1. This is what the question is asking, that you have already loaded. Remember, in this circuit, what you have done? This is 0, 1, 0, 1. Okay, this is 0, 1, 0, 1. So you have already loaded. This is 0, this is 1, this is 0, this is 1. Okay, now what we are saying? We are saying that now for how long you have to keep shift equal to 1, so that this can become 1. Okay, for how many clock cycles I need to keep shift equal to 1, so that this can become 1. I hope you understood the question. Please read the question. This line you read, very simple line, that after that data has been stored in the register. This data you have already loaded in the register. Now after that, for how many consecutive positive edges, how many clock cycles basically, we need to keep shift equal to 1 so that this signal can become 1. This is what the question is asking. Okay, so let's see. Now what we are doing, we are making shift equal to 1. This is what we are making. After making this shift equal to 1, you can notice that this input, okay, remember, for this multiplexer, because this is a multiplexer, right? This is a multiplexer, this is multiplexer. So you can see when I put shift equal to 1, then you can see this input will be going to the output. I can say this input line will be connected to the output. Okay, this input line will be connected to the output. This input line will be connected to the output. Okay, yes or no? Very simple, because these are the multiplexer and this is the select input. This shift signal, this is the select line of all the multiplexer. So if you put shift equal to 1, then this one input will be going to the output. One input will be going to the output. One input will be going to the output. Here also this one input will go to the output. Okay. Now very simple. Now let's see. Now in this question, let's see. So one thing you can easily notice, that your D2 is equal to what? See, D3 is always 0 as long as shift equal to 1. Please notice, as long as shift equal to 1. If I make shift equal to 1, if I make this shift signal equal to 1, then notice what will happen. This D3 will always be 0. Yes or no? You can notice this D3, this will always be 0. This will always be 0. Okay. What will be D2? Please tell me what will be D2? This D2 is basically Q3. Yes or no? D2 is basically Q3. So you can notice D2, that is basically Q3. Okay. What about D1? Please tell me, what about D1? What about D1? Let me know. So this D1 will be basically Q2. Yes or no? D1, that is basically Q2. And you can see that this D0, what will be D0? D0 is basically Q1. Yes or no? D0 is basically Q1. So you can see D0, that is basically Q1. Okay. So these are the, when shift is equal to 1, then this will happen. Yes or no? Okay. I hope you understood. Now initially what is the situation? Initially you can see this Q3, Q2, Q1, Q0. Okay. Initially what is there? And initially what is D3, D2, D1, D0. Okay. Notice one thing. Initially this D3, D2, D1, D0, these values, okay, these D3, sorry, let's see. Initially what is the value? Initially, I am asking initially D3 is basically 0, you can see, and D2 is 0, 1, 0, 1. Yes or no? This is the initial situation, 0, 1, 0, 1. I am saying that this was the initial situation. Okay, when shift was 0. So please understand, this was the situation when shift was 0. Now you are making shift equal to 1. This was initially. This was initially. This was the initial situation. Okay. And your Q3, Q2, Q0, that also was, you can see, that also was 0, 1, 0, 1. Okay. So basically, I am saying that this was the initial situation. Yes or no? This was the initially when shift was 0. Okay, when shift was 0. Initially when shift was 0. Now what you are doing? Now you are making shift equal to 1. Okay. Now we make shift equal to 1. Okay, so when you make shift equal to 1, now what will happen? Now you can notice this will happen. When you make shift equal to 1, then this is going to happen. Please notice. We have already seen this, that when you make shift equal to 1, then D3 will become what? Okay, now D3 will become what? You can see D3 will become 0. Okay, D3 will become 0. You can see 0, 1, 0, 1. This was the initial situation. Now when you make shift equal to 1, then this is going to happen that D3 will always be 0. Okay, and you can see D2, D1, D0. They are Q2, Q3, Q2, Q1. Okay, so they are basically 0. Yes or no? This is the situation. Okay, yes or no? When you make shift equal to 1. So when you make shift equal to 1, then this will happen. Remember, when you make shift equal to 1, as soon as this will happen when we make shift equal to 1. When we make shift equal to 1. Okay, now after the positive clock edge, because remember this is a synchronous circuit. Look at this circuit. This circuit, if you look at, this is a synchronous. There is a clock here. Okay, this is positive edge triggered, positive edge triggered, positive edge triggered. So all the flip-flop, they are positive edge triggered. This is a synchronous. This is a synchronous circuit. Yes or no? So this is a synchronous circuit. Okay, and there is positive edge triggered clock. You can see all the clock. You can see the clock is positive edge. The flip-flop is positive edge triggered. The clock is not positive edge triggered. The clock is clock, but the flip-flop is positive edge triggered. All the flip-flop, they are positive edge triggered flip-flop. Okay. Now what will happen after the first clock cycle? Tell me. After the first clock cycle, what will happen? When the clock cycle will come? After the first clock cycle, what will happen? You can see these will become the output. Okay. Yes or no? So this 0, 0, 1, 0, this will become the output of the flip-flop. This is going to become the output of the flip-flop. Okay. Now what these inputs will become? These inputs, D3 is always 0 and you can see 0, 0, 1. Okay, because notice here D3 is always 0. Please focus on this. D3 is 0, D2 is Q3 and D1 Q2, D0 Q1. So it's like this, that D3, D2, D2, D1, D0. Notice D3 is always 0. That is fixed. That is always 0. And Q3 will be D2. Okay, Q1 will be, I can say Q2 will be D1 and Q1 will be D0. Okay, yes or no? So very simple. So this is what we are saying, that this D3 is 0 and this 0, 0, 1. This will be the inputs. Okay, these will be the D inputs. Now in the next clock edge, what will happen? After the next clock edge, what will happen? Very simple. Okay, these will become the output of the flip-flop. Okay, these will become the output of the flip-flop. So you can see 0, 0, 0, 1. This will become the output of the flip-flop. Now D3, that is 0. And this will become 0, 0, 0. Now the output of the flip-flop, you can see in the next clock edge. In the next clock edge, this will become the output of the flip-flop. Okay. So now notice one thing. What is our target? We want to make 0 select. So this 0 detect equal to 1. What is this 0 detect? Notice one thing. This 0 detect. This is equal to what? There is an AND gate here. There is an AND gate here. Okay, you can see this input is Q3 bar. So 0 detect is equal to Q3 bar, Q2 bar, Q1 bar, Q0 bar. Yes or no? Is this clear? What is this 0 detect? This signal, this 0 detect, this signal. You can see Q2 bar, Q1 bar, Q3 bar. So remember 0 detect is equal to Q3 bar, Q2 bar, Q1 bar, Q0 bar. So when it will be 1? When it will be 1? We want to make it 1. 0 detect. This 0 detect, this is equal to Q3, Q2, Q1, Q0. This bar, this bar, this bar, this bar. Okay. Now when this will be 1? This 0 detect. This will be 1. This will be 1. Okay. If and only if when Q3 must be 0, Q2 must be 0, Q1 must be 0 and Q0 must be 0. Yes or no? All these things must happen. This and this and this. All these things must happen. Now you can notice they have happened. Yes or no? Now you can notice here that this is done. So at this situation, what will happen? When all of them are 0, Q3, Q2, Q1, Q0, when all of them are 0, now here this 0 detect will be 1. Here this 0 detect will become 1. And this is what we want. This is what we want. So answer will be what? So the answer will be 3 positive edges. Yes or no? The answer will be 3 positive edges. Is this clear? See, the question is very simple. Initially, this is the state of the circuit. Initially, this is the state of the circuit. And initially, when the shift is 0, then these are the D inputs of the flip-flop. Okay. Now, when you make shift equal to 1, see, this was the situation when shift was 0. This was the situation when shift was 0. Now, when you make shift equal to 1, as soon as you make shift equal to 1, then the flip-flop inputs will become 0, 0, 1, 0. Okay, this is the situation. Yes or no? When you make shift equal to 1, as soon as you make shift equal to 1, as soon as you change the signal of shift from 0 to 1, what will happen? This is going to happen. You can see D3 will be 0, D2 will be Q3, D1 will be Q2, D0 will be Q1. So this is what I am saying. Okay, yes or no? D2 will be Q3, D1 will be Q2, D0 will be Q1, and D3 is 0. So you can see as soon as you make shift equal to 1, then these will be the flip-flop inputs. In the next clock is, what will happen? After the positive clock is, what will happen? Because all the flip-flop, they are positive as triggered. So after the next positive clock is, this will be the state of the circuit. In the next positive clock is, this will be the state of the circuit. And after the next positive clock is, this will be the state of the circuit. And when Q3, Q2, Q1, Q0, when they become all 0, then this 0 detect will become 1. And this is what the question is asking. So the answer will be 3 cycles. So for this question, the question is asking, the answer will be 3 cycles. Okay. So this is a very simple question. This is not complicated. It is an easy question actually. So I hope you understood this. Yes or no? Understood? Let me know. Now let's solve this question. This is another very beautiful question in this test. Okay, so let's solve it. Let f, g be two propositional formula. Are they propositional variable? F, g, are they propositional variable or are they propositional formula? They are propositional formula. They are not propositional variable. See, let me tell you. Let me give you this point, this comparison of Boolean algebra and propositional logic. See, in the propositional logic, there is a propositional variable, right? There is a propositional variable. This propositional variable, you can understand this is same as your Boolean variable. This is same as your Boolean variable. Okay, remember, propositional variable is same as your Boolean variable. And propositional formula, that is same as what? That is Boolean formula, or I can say Boolean function. Propositional formula. What is propositional formula? That is same as your Boolean formula or Boolean function, or I can say Boolean expression. You can call Boolean expression, or you can call Boolean function, or you can say Boolean formula. Okay, yes or no? So remember very simple point that your propositional variable is same as Boolean variable and your propositional formula is same as Boolean function or Boolean formula. Now let me ask you a question and you tell me. Now you tell me, if I tell you that ABC are Boolean variable, if I tell you that they are Boolean variables, then in the truth table how many rows will be there? If I tell you ABC are the Boolean variables, now in the truth table how many rows will be there? I am telling you ABC are the Boolean variables. These are the Boolean variables. Now if you create the truth table of any Boolean function over these variables, these are the Boolean variables over these variables. If you create the truth table, then how many rows will be there? Then there will be total 8 rows. Yes or no? This is what you are going to do. Now you tell me, if I give you that E, F, okay, or maybe even E2, or maybe even E2. If I tell you that even E2 are Boolean functions, if I tell you even E2 are Boolean functions, now will you create 4-row truth table? Tell me. I tell you that even E2, or maybe let me call it F1, F2. Okay, let me call it F1, F2. If I say that these are Boolean functions, now how many rows will be there in the truth table? Now how many rows will be there in the truth table? This is F1, this is F2. Can you tell me how many rows will be there in the truth table? Let me know. Let me know. Please tell me. F1, F2, these are Boolean functions. These are Boolean expressions. Okay. So now you tell me how many rows will be there in the truth table. Will you say 4? Will you say 4? No, you will not say 4. Yes or no? Basically, maybe F1 is this. Maybe f1 is a function of abc. Yes or no? Maybe f1 is a function of abc. And maybe this is ab or ac. And maybe f2 is a function of abc. And that is maybe ab or c. Yes or no? Now you tell me, in the truth table, how many rows? What will be the number of rows in truth table? Now tell me the number of rows in the truth table. That will be 8. Yes or no? Is this clear? Now did you understand my point? I am simply telling you that propositional variable is same as Boolean variable. Propositional formula is same as Boolean expression or Boolean function. Okay. Now in this question, f, g are propositional formula. So how many rows will be there in the truth table? Can you tell me? Can you tell me? F, g are propositional formula. So tell me, how many rows will be there in the truth table? F, g are propositional formula. Let me know. How many rows will be there in the truth table? We don't know. Yes or no? We don't know. Is this clear? Okay, is this clear? Please understand that. See, if I give you these propositional variable, like let's assume that some propositional variables I give you. Let's assume P, Q, R. These are some propositional variables. Now on these variables I can create formula. I can create propositional formula. Okay, I can create propositional formula. For example, I can create this formula F, which will be P or QR. Yes or no? I can create this formula G, which is P bar. Yes or no? Agree? Or maybe what I can do F equal to P and maybe G equal to P bar. Yes or no? Is this clear? Maybe this is like P or Q and this is P or Q bar. So are you getting my point? So please understand that propositional variable, propositional formula. Understand the difference between these two. Now I am saying that f, g are propositional formula. These are propositional formula, please understand. So maybe I don't know, maybe f has variables. Maybe f has these variables p, q, r, s. Maybe g has these variables p, q, r, s. I don't know. Are you getting my point? I don't know how many variables are there. Is this clear? Is this understood to everyone? That these are propositional formula. These are not propositional variable. Okay. So remember f, g are formula. So will you make, remember one thing. Okay, let's see the difference. If I say that p, q, r, if I say these are propositional variable, then what you are going to do? If I say these are propositional variable, then this is how you are going to create the truth table. Your truth table will be something like this. Yes or no? Your truth table will be something like this. Something like this. That there will be total 8 rows in the truth table. Now, but if I say that f, g, these are propositional formula. Okay, these are propositional formula, means these are basically similar to Boolean function. These are similar to Boolean function. Remember, these are just same as Boolean function. Okay, now in this situation, remember, you are not going to create the truth table like this, right? Yes or no? You are not going to create only four rows. Okay, yes or no? Like 0, 1, something like this. Will you do that? Okay, you are not going to do that, right? This is not what you will do. This is not what you will do. What you will do? You will say that, okay, there may be some variables. Yes or no? There may be some variables, and these are the formula. Yes or no? There may be some variables. These may be proposition variable, which we don't know. These may be Boolean variables, which we don't know. Okay. So remember, there can be 2 power n rows. There can be 2 power n rows. And these are your formula. So this is the idea. Okay. Once you understand the idea, now let's solve this question. Now you can easily solve this question. So let's start. So let's see the first option. Option A. If f or g is tautology, then at least one of them is tautology. Okay, the question is saying if f or g is tautology, then at least one of them is tautology. Now, again you understand the difference between tautology and true. See, again you understand the difference between tautology and true. For example, if I say that P or Q is true, if I say P or Q is true, then can I say one of them will be definitely true? If I say P or Q is true, if I say that P or Q that is true, then can I definitely say that at least one of them is true? Tell me, can I say at least one of them is true? Please tell me, can I say at least one of them is true? Yes, I can say that, right? I can say that. But remember, if I say F or G is a tautology, if I say that F or G is a tautology, okay, now remember F or G that is tautology. Tautology means always true. Tautology means always true. That is the difference between true and tautology. So understand true versus tautology. Okay, true versus tautology. Remember, tautology means always true. What is the difference between true versus tautology? Understand the difference between true versus tautology. Okay, what is the difference between true versus tautology? Tautology means always true. Means for every combination true. For every input combination true. For every input combination. For every input combination true. Yes or no? And what is true? This is just a truth value. This is just a truth value. This is just a truth value. Okay, so remember, it's like this. If this G is tautology, then it means this is always true. Okay, if this G is a tautology, then for every input, okay, A1, A2, A3, AN, if this G is tautology, then this will always be true. Okay, is this clear? So this is the difference. I hope you understood. Okay, and this true, this is just a truth value. For example, this is just a truth value. You can see here you have your true. This is your true, which is a truth value. Okay, so now after understanding this, you can easily solve option A, that is saying if F or G is tautology, then at least one of them is tautology. See, this is very simple false. Option A is saying that if F or G is a tautology, F or G, that is saying that this is tautology, then can I say at least one of them will be tautology? Then can I say at least one of them will be tautology? See, this statement is different from this statement. Here notice I am saying P or Q is true. P or Q is true. Then at least one of them will be true. Yes, that is correct. Okay, yes, that is correct. Yes or no? But remember, understand this statement. F or G is tautology. F or G is tautology means F or G is always true. Now can I say F will be tautology or at least one of them will be tautology? No. Okay, then at least one of them will be tautology. That is not necessary. Let me give you counter example. For example, okay, let me give you counter example. Let me give you this counter example. Take F equal to P and take G equal to P bar. Yes or no? Now you can notice this is not tautology, this is contingency. Right? This is contingency. This is also contingency. Okay, both these are not tautology, right? F comma P. But you can notice F or G. Notice F or G. That is a tautology. Notice F or G. That means P or P bar. That is always true. That is always true. That means that is tautology. Understood? Okay, so this statement 1, that is false. Yes or no? Is this clear? Statement A, that is false. Okay, understood. See, very simple point. F or G is given to you as tautology. So this is how you can do the analysis. Let's do the analysis like this. Okay, so these are the formulas and maybe these are the propositional variables. Okay, remember there are 2 power n rows. Now what you are saying? You are saying that F or G is tautology. You are saying F or G is tautology. That means it will be always true. Okay, yes or no? It is going to be always true. So now you tell me, is it necessary that this is always true or this is always true? Is it necessary? See, this is always true. This is given to you that this is tautology. The question is saying that this is tautology. Okay, this is what the question is saying. Now you tell me, is it necessary that F should be tautology or G should be tautology? No. For example, what you can do, you can make false here, true here. You can make true here, false here. You can make false here, false here. You can make true here, true here. You can make false here, true here. Are you getting my point? You can make false here, true here. So can you notice that this F, this G, you can see this F is also not tautology, G is also not tautology. Okay, understood? So is this clear? Option A, is that clear? Option A is false. What about option B? If F and G is contradiction, then at least one of them is contradiction. If F and G is contradiction, option B. What option B is saying? Option B is saying that F and G is contradiction. F and G, that is a contradiction. Then can I say at least one of them is contradiction? If that is contradiction, then can I say at least one of them is contradiction? Again, no. Again, I can give you counter example. For example, you can take F equal to P, G equal to P bar. This is not tautology, this is contingency. Yes or no? This is not tautology, this is a contingency. This is not tautology, this is also contingency. Right? Both of them are contingency. But you can notice F and G, P and P bar, that is a contradiction. That is a contradiction. So can you notice option B, that is also wrong. Option B is also wrong. Understood? Is this clear? This is a beautiful question, let me tell you. This similar type of question has come in the GATE 1991. In the GATE 1991, a similar question has come. You can check it out. GATE 1991 proposition formula question. Just check it out. Propositional formula question. Propositional formula question. Okay, just check it out. Okay. Let me tell you one thing. This GATE 1991 question on proposition formula, you check it out today. Okay. Check it out on the GATE Overflow website. On the GATE Overflow, you check it out. For this question, let me tell you, many students, they get the correct answer by wrong method. By a wrong method, they get the correct answer for this question. Okay. So you can just check it out. Anyway, now let's see this option B. So see this option B, another analysis. F and G is given to you as contradiction, right? The question is saying that F and G is contradiction. Okay, so what you can do? You can do analysis like this. See, these may be the propositional variable because this is a formula, this is a formula. So these are the propositional variable over which these formulas are defined. So you can see there are 2 power n rows. Now, the question is saying that this is contradiction. The question is saying that this is contradiction. Means this is always false. False, 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 and so on. Okay, this is always false. Now in this situation, see this is possible. For example, in this row, in this particular row, you can notice F is true, G is false. That is correct. Okay, maybe in the next row, what can happen? F is false, G is also false. In the next row, maybe what can happen? That F is false, G is true. Okay, yes or no? So you can notice that G is not a contradiction, F is not a contradiction. Okay, so like this you can analyze. So option B is also not correct. What about option C? Please tell me. If F implies G is tautology, then either F is contradiction or G is tautology. Is this true? Is this true? Tell me. Option 3 is saying that F implies G is a tautology. This is given to you as a tautology. Okay, this is what is given to you. That F implies G, that is tautology. This is F, this is G. The question is saying that F implies G, that is always true. Yes or no? That is always true. And maybe these are the propositional variable. So you don't have to worry about it. Okay, so now the question is saying that this F implies G, this is tautology. Means this is always true. This is always true, right? Now in this situation, what is possible? For example, see, this is possible, right? Maybe in this row, both F and G are true. Okay, in the next row, maybe both are false. In the next row, maybe this is false, this is true. Yes or no? Are you getting my point? Okay, So like this, like this. Now you can notice here, F is not a contradiction. Please notice F is not a contradiction and G is not a tautology. Here you can notice F implies G is tautology. This is tautology. But you can notice F is not a contradiction. Also, G is not a tautology. Yes or no? So I can easily say that option C, that is also false. Okay, option C, that is also false. Is this clear? Okay, understood? I can give you a counter example also for option C. Let me give you for option C. For this option C, this is saying that F implies G. This is a tautology. Okay, this is a tautology. So now what you can do here, you can assume that F is a P and you can assume G is also P. Now you can notice F is P, so this is contingency, this is not tautology, right? F is P, so this is not a tautology. G is P, that is also not a tautology, that is also contingency. Now in this situation, but you can notice F implies G, what that will be? F implies G means P implies P. P implies P, that is a tautology. P implies P, that will be a tautology. That will be tautology. Okay, so very simple. So I hope you understood this. So the option C is also not option C is also wrong. Finally, F implies G is contradiction. Then F is tautology and G is contradiction. Can you prove it? F implies G is contradiction. Then F is tautology and G is contradiction. Can you prove it? Yes, we can prove it, right? Okay, let's see option D. The question is saying that F implies G is contradiction. This is a contradiction. Now what you can say about F comma G? Now what you can say about F comma G? Tell me. F, G. Okay, we are saying that F implies G is contradiction. This is contradiction means this is always false. This is always false. Now you tell me. In this row, look at the first row. Look at the first row. If I want F implies G to be false, then how many choices I have for F comma G? Tell me. I want F implies G to be false. I want this to be false. Now you tell me, for F comma G, how many choices I have? There is only one choice. This must be true. This must be false. Now look at the second row. Look at the second row. Look at the second row. This must be true. This must be false. Look at the third row. This must be true. This must be false. So can you notice that F must be tautology? F must be tautology and G must be contradiction. F must be tautology and G must be contradiction. Yes or no? F must be tautology and G must be contradiction. So option D is correct. So option D, that is correct. Understood? Let me know. Is this clear to everyone? So this is your question. This is another beautiful question. I hope you found this beautiful. Okay, because I can tell you one thing. You can search. There is a GATE 1991 question on propositional formula. You can search it on the GATE Overflow website. Go to the GATE Overflow website for this question and you can easily find out that this question many students are solving by wrong method. Means they are getting the correct answer but their method is wrong. Their understanding is wrong. But they are getting the correct answer. Now you can notice with the same understanding, with the same concept, if they solve this question, then they will get wrong answer. They are going to get wrong answer. So that is the reason I am saying that this is a beautiful question. I hope you understood some concepts. Please tell me, did your understanding improve for some concepts? Did you learn something new in this question? Let me know. So you can see there are 7 upward in this question. So students loved this question. Whenever you find some beautiful question, then please upvote. Okay. Is this question clear to everyone? Now, let's solve this question. Basically, a strongly connected component question is there. A graph is given to you and the question is, first the definition of strongly connected component is given to you. Then the definition of DAG of strongly connected component, that is given to you. Okay, see, very simple point. First, strongly connected component definition is given. Then here, look at this. Here what is given to you? Here the definition of DAG, directed acyclic graph of strongly connected component. This is given to you. Okay, so both the definitions are given. Here strongly connected component definition is given, and here directed acyclic graph of strongly connected component, this definition is given. Now this graph is given to you, and the question is asking you that in this directed acyclic graph, of strongly connected component, how many vertices are there and how many edges are there? How many vertices are there? How many edges are there? The question is asking what is A plus B. Okay. Now, let me tell you that actually this concept I have already explained in these videos. So you can just watch it. I have already provided the link under this question in the answer. You can see. You can watch strongly connected component concept. You can understand what is this concept. You can also understand what is DAG, directed acyclic graph of strongly connected component in this video. I will provide you the link in the description. Okay, don't worry. I will give you the link in the description. So you can just check it out. The description, you can check it out. I will provide you link in the description. So you can watch this video, you can watch this video. After that, this question will become very easy for you. Okay. Basically, in this graph, you find what are the strongly connected component, and then you make their directed acyclic graph. Okay. So finally, your answer will be this. You can see this is your final answer. So number of vertices will be 4. Actually, every vertex is a strongly connected component. You can see this is a strongly connected component in this graph. If you look at this graph, in this graph, you can see that A is a strongly connected component. Okay. Also BDEH. Okay. BDEH. This is also a strongly connected component. This. Okay. So you can just check it out. These videos you can just simply watch. Okay. I will provide you the link in the description. So don't worry about it. You can watch. Okay. And you can easily solve this question. Okay. So I think this is enough for today. Okay. So there are some questions which are remaining. If you have doubt in these questions, you can put a comment. I will provide you detailed solution. Okay. So for example, this question is there. For this question already the solution is provided. Okay. There is a generating function question. This question is based on the generating function. So for this question, the detailed solution is already provided. You can check it out. If you have any doubt, please put a comment. I will provide you the solution. Okay. So because on the 10th February, there is GATE exam. Okay. After 3 days, right? Okay. Only 2 days. Sorry. After 2 days, there is GATE exam, GATE computer science exam. So I'm not going to provide you the part 2 solution. Okay. Because you should do the revision. See, GATE exam is coming and you should focus on the revision. Now, if you have any doubt in any question of All India Mock Test 5, if any remaining question you have any doubt, then please put a comment on the GATE Overflow website. Okay, on the GATE Overflow website, under the question, put a comment. I promise you, I will provide you detailed solution. The text solution I will provide you, but I will provide you all the details. Okay, so you will not have any doubt in that question. If you have any doubt, you can just put a comment. And I will give you the detailed text solution. I will reply to you and I will give you the detailed solution. Okay, so thank you everyone. I hope you loved this session. Please tell me. All the complicated questions I have taken actually, you can see. Okay, from the beginning, I have taken all the complicated 2-mark question I have taken. In this All India Mock Test 2, in this All India Mock Test 5, all the tricky, all the complicated questions, those I have taken in this session. Some easy questions are remaining, very easy questions. Those you can do. Okay. So please tell me, anyone has any doubt? Did you love this session? Also, I hope you loved our All India Mock Test. This year for GATE Computer Science 2024, we conducted 5 All India Mock Tests. And all these All India Mock Tests, they have original questions, standard questions, original question, unique questions. Okay. These are not replica of the GATE exam questions. Like if there is a GATE exam question, just change the value and we give to you in the All India Mock Test. We did not do that. Okay. So basically in our test, in goclasses mock test, we have provided you unique question in every test so that every question will improve your knowledge. Each and every question is going to improve your knowledge, is going to improve your understanding. Okay. So that is that was our motive. And that is what we have done. We have provided you unique questions, standard questions, good quality questions, and we have provided you detailed solution, either detailed video solution or detailed text solution. So for every question, we have done the discussion. Okay, I hope you loved it. Please put a comment under this video and please share your feedback about All India mock test that we have conducted. Okay, did you love it? Did you love this session? Let me know in the comments. Please put a comment. So please press the like button and please put a comment. Okay. Thank you everyone. Some students are saying go classes, everything is unique. Thank you. A student is saying go classes is love. So thank you Asutosh. Thank you Raju. Thank you so much. So please put a comment and please press the like button. Okay, thank you. And all the best for the GATE exam. Okay, we will meet. Don't worry. Before the GATE exam, one day before the GATE exam, we will meet live. We will meet. We will discuss with you how to attempt the GATE exam. What are the things that you need to take care. Okay, so we will invite our previous year toppers, go classes, GATE 2023 toppers. We will invite and you can ask them any query, any doubt. Okay, so one day before the GATE exam, that is 9th February. On the 9th February, we will come live. A live session we will do and we will invite our go classes 2023 toppers. We will invite. Okay, thank you.